The objective of this video is to develop Bode plots for the canonical form of poles, zeros, inverted poles, and inverted zeros. So I want you to create this as a nice table or a nice set of notes in your notebook that you can refer back to. We're going to be drawing the Bode plots for these fundamental forms of zeros, poles, and inverted poles that we define the transfer functions for at the beginning of this controls unit. And so this is going to form a fundamental building block that you can use to quickly construct Bode plots of transfer functions when you're given an arbitrary transfer function. Or you can use this in the reverse way. You can use this in the design fashion, that if you know you have a desired transfer function, you have a desired Bode plot of a transfer function, you can use this set of notes that we're about to create to construct the mathematical form of the transfer function. So you're going to be able to recognize the graphical depiction of a transfer function and extract from your graphical depiction what the equation for your transfer function is. Alright, so we'll go through this one by one, starting with the simplest case, which is a 0 at the origin, and the transfer function of this, h of 0z, is equal to s over 2 pi, where 2 pi is just for convenience, so that we can say that h of j omega is equal to jf. So clearly, if we were to plot this transfer function, it is going to be increasing at a rate of 20 decibels per decade, and at f equals 1 hertz, it's going to be 0 decibels. At 10 hertz, it's going to be 20 decibels. So at infinite frequency, it's going to have an infinite value, and at DC conditions, it's going to be at negative infinity decibels. The phase of this is constantly at 90 degrees. We can build upon this to consider a pole at the origin. And for the case of a pole at the origin, we can recognize that it's 1 over the transfer function for our 0 at the origin, so we can use our graphical technique of inversion to create this, or we can just recognize how to plot it from its simple form. Okay, building up from these towards slightly more involved transfer functions, we can talk about a left half plane 0. And we can use our mathematical operation by first considering the Bode plot of 1 and adding that to the Bode plot of s by omega z, which is going to be the simple case of a 0 at the origin. And if we do this addition operation, we always take the larger of the two transfer functions, and we end up with a Bode plot that looks like this. And we can similarly see that if we're plotting the phase angle, we're going to start at 0 degrees until we get to 0.1 times our 0 frequency. Then we're going to start increasing, and we're going to end up at 90 degrees when we're a decade past our 0 frequency. And at the frequency of our 0, we're going to be at 45 degrees. We can also talk about a right half plane 0. And we'll notice immediately that this has the same magnitude plot, but a different phase angle plot. And the phase angle plot, it starts at the same 0 degree point, but it goes down to negative 90 instead of up to positive 90. So we can notice that for both of these transfer functions, our Bode plot always starts at 0 decibels and at 0 degrees. And by starting, I mean at the low frequency regime, the Bode plot for our 0 always begins at 0 decibels, stays at 0 decibels until we get to the 0 frequency, and then begins increasing at 20 decibels per decade. Whereas the phase angle always begins at 0 degrees, stays at 0 degrees until a decade below our 0 frequency, and then increases to 90 degrees over 2 decades, or in the case of a right half plane 0, decreases to negative 90 degrees over 2 decades. let's now talk about the inverted left half plane 0 and the inverted right half plane 0. And so while the left half plane 0 looked like the summation of 1 and a 0 at the origin, the left half plane 0 looks like the summation of 1 and a pole at the origin. So remember what a pole at the origin looks like. We had this Bode plot here for a pole at the origin. So we start off decreasing at negative 20 decibels per decade, and we start off with a phase of negative 90 degrees. And so in this case, we'll again draw the graphical interpretation for how we constructed this. So we have the Bode plot of 1 is 0 decibels and an angle of 0 degrees. And the Bode plot of omega z by s is constantly decreasing. So when we add these two, we take the larger of the two paths, and we have a transfer function that looks like this. So our decibel plot looks like that. Now our phase angle plot is going to start off at negative 90 degrees at the low frequency regime. And a decade below the inverted 0, we're going to start increasing, and we'll increase to 0 degrees over 2 decades, so that at the 0 frequency we will be at 45 degrees. And for an inverted right half plane 0, we have the following transfer function, which will again have the same magnitude plot, but the phase angle plot is going to be the opposite. We're going to start at 90 degrees, and at a decade below our 0 frequency we'll start decreasing, and we'll decrease all the way to 0 degrees over 2 decades. So you can see that while for a left half plane 0 we start at 0 decibels and at 0 degrees, in the case of an inverted 0, we always end at 0 decibels and 0 degrees. And this is an important property of these plots, of the inverted versus the non-inverted zeros. And I want to show you one other thing about this. So we can note that when we have our transfer function for a left half plane 0, and I could similarly be showing this for the right half plane 0, you have this transfer function, which you can manipulate to get in terms of a pole at the origin and a simple left half plane 0 in the numerator. And so we actually have this equivalency. It's mathematically equivalent. You can write it either way, and it becomes the same thing. And so the question is, why even define the idea of these inverted poles and zeros? Because when you're looking at a transfer function and you want to have it have a certain gain at a high frequency, you can then express it as an inverted left half plane 0. Or if you want it to have a certain gain at the low frequency, you express it as a simple 0. So you have this equivalency that we'll be making use of in future videos for this class and future discussion in this class. So I want to get you thinking about this right now, that an inverted left half plane 0 or an inverted right half plane 0 is equivalent to having a 0 and a pole scaled by a certain magnitude. And the reason that we define it is for convenience when we're drawing our Bode plots and going between a Bode plot and a transfer function. It allows for easier math. So it's a tool. Next, we're going to talk about poles. So left half plane pole, right half plane pole, inverted left half plane pole, and inverted right half plane pole. So the transfer function for our left half plane pole is 1 over 1 plus s by omega p. And that is in fact just equal to the inversion of a left half plane 0. So we just took this transfer function here and we inverted it. And we know what the graphical operation is for that. We just subtract it from 0 decibels. And so we can use that mathematical operation to construct our Bode plot, or we could build it up as we did for the zeros. In this case, I'm just going to quickly sketch it. And if you go back to your notes and you look at what the left half plane 0 looks like, you can see easily how the mathematical operation was to convert this into a left half plane pole. And so similarly, we'll do the same thing for a right half plane pole. And we again have the same magnitude, but our phase plot looks different. So we can make the observation that in these cases, the plots start at 0 decibels and 0 degrees, and they end at something else. So similarly to our left half plane zeros, which start at 0 decibels and 0 degrees, our simple poles, our left half plane and right half plane poles, start at 0 decibels and 0 degrees. And also similarly to the zeros, the way you recognize whether the transfer function is a left half plane or right half plane pole, you look at the phase plot. For the case of inverted left half plane poles and zeros, you finally end up with this Bode plot. And we can remark that both of these transfer functions end at 0 decibels and at 0 degrees. So we again have this duality where where a pole, a simple pole, starts at 0 decibels and 0 degrees. Inverted pole ends at 0 decibels and 0 degrees. And we can note, similarly to the case of zeros and inverted zeros, we can show an equivalency. So note that when we write out our transfer function for our inverted pole, an inverted pole is equivalent to a normal pole and a 0 at the origin. So an inverted pole is equivalent to a normal pole at the same location times a 0 at the origin and then scaled by a certain magnitude. So again, the reason that we introduce the notion of an inverted pole or an inverted 0 is so that we can easily extract the transfer function mathematical expression from a Bode plot. So if you happen to be given a Bode plot and somebody tells you what the gain is in the high frequency, it'll be very convenient for you to use these inverted poles and zeros to extract the mathematical representation of it, because these inverted poles and zeros are always at 0 decibel in the high frequency range. Whereas if somebody gives you a Bode plot and gives you the gain at the low frequency regime, it'll be much easier for you to use regular poles and zeros to extract out the mathematical representation of the transfer function, because normal poles and zeros begin at 0 decibels. So this is completely for mathematical convenience. Your world could consist only of poles and zeros and you'd have the complete picture. You would just do more work to extract your mathematical representation of a transfer function.